Hello chemistry students, in this video I'm going to go over Le Chatelier's principle. Alright, so Le Chatelier's principle states that when you stress a system in equilibrium, it will respond in a way such that the system will return to equilibrium. Alright, so here are some ways that you can stress the equilibrium. So you can add or remove reactants, you can add or remove products, you can increase or decrease the pressure of the products or the reactants, or you can increase or decrease the temperature. So let's take a look at what changing the concentration of the reactants does. So if the concentration of a reactant is increased, then that means that you're going to have to form more product to return to equilibrium. So that's what we refer to as a shift right. If you're forming more product, that means you're forming more of something on the right side of the equation, so you're shifting right. If you decrease the concentration of reactant, then some of the product's going to have to reform reactant. So that's what's going to be needed to reestablish equilibrium. So that is called a shift left. So if you form more product, then you shift right. If you form more reactant, then you shift left. All right, if you play around with the concentration of products, so if you increase the concentration of a product, that makes you have too much product. That means that some reactant will have to form, so that's going to cause a shift left. If you decrease the concentration of a product, then some of the reactant would have to be used up to form more product to reestablish equilibrium. So that's going to cause a shift to the right. This is a common approach used to increase the yield in commercial chemical processes. They figure out some kind of way to remove the product so the reactants will keep on reacting, making more product. Alright, so let's look at some examples with a real chemical reaction here. So we have this reaction where H2 and I2 react to make 2HI. So we're going to predict the changes in equilibrium produced, or the shifts in equilibrium produced by the following changes. So if we add some H2, well, if we add H2, then that means now we have too much reactant. So in order to take care of that, we need to increase products and decrease reactants to make equilibrium reestablish. So that is going to result in a shift right as more product forms to reestablish equilibrium. Okay, how about if we add some I2? So that will also add a reactant, which means that we will need to form more product to reestablish the balance of equilibrium. So that's also going to be a shift right. So basically if you add a reactant, then the equilibrium shifts right. If you remove hydrogen, then some hydrogen would be needed to reform to reestablish equilibrium. The only way you could reform hydrogen is if some of the product decomposes and makes more hydrogen. So that's going to be a shift left as the product is used up to form reactant. Okay, same thing with I2. I will also produce a shift left. Let's look at some examples with messing around with the product. So in this particular reaction, there's only one product, so that makes things a little bit easier. Alright, so if we add some HI, that's going to make it so that there's too much HI at the equilibrium, or for there to be equilibrium, so some of it will have to decompose. So the product is going to change into reactants, and that results in a shift left. If you remove HI, then the products will, or excuse me, the reactants will react to form product, and that will result in a shift right. Okay, pressure can also affect the equilibrium position of a reaction. So just like with reaction rates, changing the pressure only significantly impacts gases. So if you increase the partial pressure of all the gases present, then the side with the fewer total number of gas moles will be favored. So let's look at some examples of that. Still using the same reaction for this first example. So first off, let's talk about what happens when you increase or decrease the pressure on this reaction. So let's look at how many moles of gas we have. We have 1 mole of H2 gas, we have 1 mole of I2 gas, and then on the other side we have 2 moles of HI gas. That means there's the same number of total moles on the left and the right side of this reaction. Well, what does that mean? It means there's not going to be a shift if you change the pressure. There's no savings in space. Think about the ideal gas law. So at the same temperature and pressure and same number of moles, these would take up equal volume. So there's no advantage to one side or the other. However, with this reaction, so we're taking nitrogen and hydrogen and forming ammonia. So on the left side, there's 4 moles, and on the right side, there's 2 moles. Now, if you think about the ideal gas law, or just Avogadro's hypothesis, the number of moles here would correspond to taking up more space, or the larger number of moles would correspond to taking up more space. So if you increase the pressure, it's going to kind of squeeze this together, and you can fit 2 moles into a space more easily than you can fit 4 moles. So if you tighten the space down, then it's going to increasingly favor the side with fewer moles of gas. Okay, so products are favored, and that's going to shift right. Well, how about if we increase the volume of the reaction vessel? Now let's think about this carefully. The first one said increase pressure. If we increase the volume, what does that do to pressure? Well, it actually decreases the pressure. Remember Boyle's law? So if you increase volume, then the pressure decreases. So if you increase the volume, that's going to cause reactants to be more favored, because opening the container or increasing the size of the container means there's more space for these 4 moles to occupy, so there's less advantage to fitting the gas into a smaller space like the 2 mole side. So that is going to result in a shift left. Alright, changing the temperature. This is my least favorite one out of the Le Chatelier shifts, but one that we need to talk about nonetheless. So, changing the temperature is the only change that actually does change the value of KEQ. KEQ is defined as being at a specific temperature, so when you change the temperature, that does change the value of KEQ. So increasing the temperature, this is going to help you understand what's going on, hopefully. Increasing the temperature adds energy to the system, while decreasing the temperature removes energy from the system. So, what that means is that endothermic reactions absorb heat, and that means that heat is like a reactant for them, so they shift right when you increase the temperature. Increasing the temperature is like adding more of a reactant, so that causes the shift to go to the product side. Exothermic reactions release heat, so heat is like a product from an exothermic reaction. So those reactions are going to shift to the left when you add heat to them. Now, there are a few disclaimers here. By the way, this is taught in lots of chemistry books, including the AP chemistry book that I use. But there's something that's kind of wrong here, because these rules only work when the entropy change is negative for a particular reaction. And the way I figured this out is I was trying to explain why sodium hydroxide becomes more soluble at higher temperatures, and you can't explain it with this. So anyways, Gibbs free energy is the better way to predict what's going to happen to the equilibrium constant with changes in temperature. But you know what? I'm teaching it anyways because it shows up, it's tested, it's all over the internet. Can't figure out why, but maybe people will just think that this is too complicated for chemistry students to figure out. Um, and you know what? I had to become a chemistry teacher for several years before I finally noticed this and was like, hey, there's something weird going on here. So anyways, let's carry on. All right, so we'll look at this first example with some nitrogen and oxygen reacting to make nitrogen oxide. So we're going to address this. The temperature is increased. This particular reaction is endothermic, so the positive enthalpy change tells us that. So the energy is like a reactant. So you could write this reaction to show the energy as a reactant. So increasing the temperature is going to add heat, which is like adding a reactant. That's going to cause the reaction to shift right as more product forms and KEQ increases. All right, here's another example. So this one is exothermic, noted by the negative delta H. So as temperature is increased, it's like adding a product. You add more products, the equilibrium would need to shift to left, and that would cause a decrease in products and increase in reactants. KEQ decreases as a result. Remember, KEQ only changes with temperature changes. That would result in a shift to left. All right, and an application of Le Chatelier's that has great consequences for civilization in general is this ammonia synthesis. So Fritz Haber, pictured here, applied it in 1909 to be able to synthesize ammonia from nitrogen and hydrogen, which are fairly readily available. Something that's interesting, though, is that ammonia can also be used to manufacture explosives. So World War II was extended because Germany would have been blocked off from their sources of ammonia nitrates to form explosives, but this process enabled them to continue manufacturing explosives and hold out a little bit longer. Fritz Haber was very much a German patriot, but he was also Jewish, and so things didn't go so well during the 1930s for him, as he kind of got pushed out of his position and eventually ended up passing away in 1934. All right, I have one last point here to make, is that catalysts do not change the equilibrium position or the value of KEQ. All they do is they speed up reactions so they reach equilibrium faster. And remember, they do that by lowering the activation energy of the reaction, but they don't change anything about the equilibrium. All right, thanks for watching.